What remains when you remove everything? Every galaxy, every star, every planet, down to every particle and atom. In this video, you will learn what the fabric of space-time actually is. If you are a physics and space enthusiast like me, you are in the right place. Let me know in the comments if you are a student or just a general viewer who is curious about this topic. Get ready to deep dive into the insane words of space-time fabrics. Imagine you open your eyes and find yourself floating in complete darkness. Not the darkness of a room at night, but the absolute darkness of deep space. There are no stars around you, no planets, no light anywhere. You try to move your arms and legs, and you realize something incredible. You are moving through something right now, something invisible, something that surrounds you completely. This thing you are moving through can bend like rubber. It can twist like a rope. Scientists have even discovered it can break and create ripples that travel across the entire universe. But here is the question that will haunt us for the next 3 hours. What is this thing actually made of? Let me show you what I mean. Watch a fish swimming through water. We know what water is made of. 2 hydrogen atoms stuck to 1 oxygen atom. H2O. Simple. Now watch a bird flying through the air. We know what air is made of. Mostly nitrogen and oxygen molecules bouncing around. Easy to understand. But now look at our planet Earth spinning through space. What is it moving through? What is space made of? Here is what makes this question so powerful. We have named this mysterious thing space-time fabric. You have heard that phrase before, right? The fabric of space-time. But think about that word for a second. Fabric. When you hold a piece of fabric in your hands, a shirt, a blanket, anything, you can see it is made of threads. Those threads are woven together in a pattern. Pull out a single thread and look closer. That thread is made of fibers. Those fibers are made of molecules. Everything we call fabric has smaller parts inside it. So, if space-time is a fabric, what are the threads? What are the fibers? What is it actually made of? By the end of this video, you will understand one of the universe's deepest secrets. You will know what the smartest physicists in the world think space-time might be made of. And I promise you, the answer will change everything you thought you knew about reality. It will change how you think about the room you're sitting in right now. It will change how you think about yourself and your place in the cosmos. But I need to warn you, this journey will take us to some strange places. We will talk about invisible dimensions you cannot see. We will explore the idea that space itself might be an illusion. We will discover that time might not flow the way you think it does. Are you ready? Then let us begin with something simpler. Let me start with something you have definitely heard before. Maybe in a science class, maybe in a movie, maybe in another YouTube video. Someone says, gravity bends the fabric of space-time. And maybe you nodded your head like you understood. But did you really understand? Have you ever stopped and asked yourself, if space-time is a fabric, what are the threads? Think about this for a moment. Every fabric you've ever touched in your entire life is made of something smaller. Your shirt is made of cotton threads. Those threads are made of cotton fibers. Those fibers are made of cellulose molecules. Those molecules are made of atoms. Those atoms are made of protons, neutrons, and electrons. We can keep going smaller and smaller, but the point is, everything is made of something. So what about space itself? What about the emptiness between Earth and the Moon? What about the vast distances between stars? What about the room you're sitting in right now, the space between you and your screen? What is that made of? Let me give you a familiar example that will help us think about this. Imagine you drop a heavy bowling ball onto a trampoline. The trampoline sinks down where the ball sits, creating a dip, a curve in the surface. Now roll a marble across the trampoline. What happens? The marble does not roll in a straight line anymore. It curves toward the bowling ball. It might even spiral around it. This is how physicists explain gravity. Massive objects like the Sun create a dip in space-time, and smaller objects like Earth curve toward that dip. But here is the part everyone forgets to ask. A trampoline is made of stretchy fabric woven from synthetic fibers. That is why it can bend. That is why it can create curves. So what is space-time made of that allows it to bend? What is space-time woven from? Watch what happens when you drop a pebble into a perfectly still pond. Ripples spread outward in circles. Those ripples are waves moving through water. Water is the medium carrying those waves. In 2015, scientists detected gravitational waves for the first time in human history. These were ripples in space-time itself, created by two black holes smashing together 1 billion light-years away. If space-time can ripple like water, what is the medium? What is doing the rippling? Here is what makes this question so beautifully crazy. Scientists still do not have a complete answer. Oh, they have ideas. They have brilliant mind-bending theories that we will explore together. But right now, at this moment in history, humanity does not know for certain what space-time is made of. This is one of the biggest unsolved mysteries in all of physics. But solving this mystery is not just about satisfying curiosity. Understanding what space-time is made of would unlock secrets about black holes, the Big Bang, and the nature of reality itself. It would complete our understanding of the universe. And the journey to find this answer involves some of the most creative thinking humans have ever done. Now, you might be thinking, this is interesting, but why should I personally care what space-time is made of? I have a job, I have bills to pay, I have a life to live. How does this affect me? Let me show you something that will blow your mind. Right now, in your pocket or on your desk, you probably have a smartphone. Open up the Maps application, that little blue dot showing your location. That dot only works because scientists understand how space-time bends. Let me explain. Your phone talks to satellites orbiting Earth about 20,000 kilometers above your head. These satellites are moving at about 14,000 kilometers per hour. At that speed and that height, something weird happens. Time itself moves differently for those satellites than it does for you standing on the ground. The satellites' clocks tick slightly faster than your clock, about 45 microseconds faster every single day. That might not sound like much, but if we did not account for this difference, your GPS would be wrong by about 11 kilometers every single day. Think about that. Every time you use GPS to find a restaurant, navigate to a friend's house, or track your morning run, you are using Einstein's understanding of space-time. Without understanding how space-time works, modern navigation would be impossible. This is not abstract theory. This is technology you use every single day. But it goes deeper than GPS. Understanding space-time is helping us detect gravitational waves, ripples in the fabric of reality, created by colliding black holes billions of light years away. These detections are not just cool science news, they are opening an entirely new way to observe the universe. For all of human history, we have studied the cosmos using light, telescopes that capture photons. But gravitational waves let us see events that produce no light at all. We are developing a completely new sense, like suddenly gaining the ability to hear after being deaf your entire life. Understanding space-time is also crucial for understanding where we came from. The Big Bang itself, the moment when all space, all time, all matter and energy came into existence, that event happened in space-time. Or did space-time itself come into existence at that moment? These are not just philosophical questions. They are questions about your origin story. Every atom in your body was forged in the heart of a star that exploded billions of years ago. That star existed in space-time. You exist in space-time. Understanding what space-time is made of is understanding the stage where every moment of your life happens. Here is another reason this matters. Black holes. In the center of our own galaxy, there is a supermassive black hole containing the mass of 4 million suns. Black holes are places where space-time is bent so extremely that it breaks the normal rules. Nothing can escape, not even light. Understanding what space-time is made of is the key to understanding what happens inside a black hole. And someday, if humanity ever wants to achieve science fiction dreams like traveling faster than light or bending space to travel vast distances, we need to understand space-time at its deepest level. But let me tell you the real reason this matters to you. Every human being who has ever lived has looked up at the night sky and wondered, what is all this? Why does anything exist? What is reality really made of? These are the questions that make us human. And right now, in your lifetime, we are closer than ever to answering one of those fundamental questions. You are living through a golden age of discovery. 50 years from now, people will look back at this era and say, that was when humanity figured out what space-time is made of. Do you want to understand what they discovered? Then stay with me. Before we dive into the deep end, let me give you a map of where we are going. This journey is long, 3 hours, but I promise you every minute will build on the last. We are not going to jump straight into quantum foam and string theory. That would be like trying to run before you can walk. Instead, we are going to build our understanding step by step, piece by piece, until the complex becomes simple. Here is how this journey is structured. First, we are going to discover what space-time actually is. Most people have a vague sense that Einstein proved space and time are connected somehow, but they do not really understand what that means. We are going to change that. You will understand exactly what space-time is and why scientists use that strange hyphenated word. Second, we will explore how space-time behaves. It can bend, stretch, compress, and ripple. We will look at real experiments and observations that prove these things actually happen. By the end of this section, space-time will stop feeling like an abstract concept and start feeling real. Third, we are going to hit a wall. We are going to discover the biggest problem in modern physics, the reason why our two best theories about reality contradict each other and cannot both be right. This is where things get interesting, because this problem is what drives scientists to ask, what is space-time really made of? Fourth, we will explore the leading answers. String theory says space-time is made of vibrating strings of energy. Loop quantum gravity says it is made of quantum loops woven together like a fabric. Other theories say space-time is not made of anything physical. It is made of pure information. We will examine each theory carefully, understanding its beauty and its problems. Finally, we will come back to where we started and ask, what do we believe? Where does the evidence point? And what experiments might finally give us the answer? I want to set some expectations before we begin. This video is going to challenge your brain. There will be moments where you feel confused. That is normal. Physics is hard, and these are genuinely difficult concepts that took the smartest people on Earth decades to figure out. But here is my promise to you. I will never use complicated math. I will never use jargon without explaining it first. And I will use so many analogies and examples that even the strangest concepts will start to make sense. Also, this journey is going to feel like a story because it is a story. It is the story of how humans went from thinking space was just empty nothingness to realizing it might be woven from invisible threads smaller than atoms. It is a detective story, a mystery story, and a story about human creativity and persistence. So here is my final question before we begin. Is space nothing, or is it something? For thousands of years, humans assumed space was just emptiness, the absence of stuff. But what if they were wrong? What if space is as real and physical as the ground beneath your feet, just invisible? Let us find out together. Chapter 1. What even is space? Close your eyes for a moment. Imagine you are floating in the middle of a completely empty room. The walls, floor and ceiling have all disappeared. There is nothing around you. No air, no light, no objects, nothing. You are suspended in pure emptiness. Now, here is my question. Is there anything there where you are floating? Or is there literally nothing? This question tortured ancient philosophers for thousands of years. The Greeks were the first to really wrestle with it. A philosopher named Aristotle, who lived about 2,300 years ago, had a strong opinion about emptiness. He said it was impossible. Aristotle believed that nature has a horror of vacuum. The universe fundamentally refuses to allow truly empty space to exist. According to him, space had to be filled with something, even if that something was invisible. Why did Aristotle believe this? He had a good reason. Imagine pushing a book across a table. It eventually stops moving because friction from the air and the table slows it down. Now imagine pushing that same book through water. It stops faster because water creates more resistance. Aristotle reasoned that if you push something through nothing, through pure empty space, it would move infinitely fast, which seemed absurd. Therefore, empty space could not exist. For nearly 2,000 years, most scholars agreed with Aristotle. They thought space had to be filled with some kind of invisible substance, even though they could not see it or touch it. They called this mysterious substance the ether, or the plenum. To them, space was not empty. It was full of this invisible stuff. But then something changed. In the 1600s, scientists started doing actual experiments instead of just thinking about things philosophically. A German scientist named Otto von Guericke built a pump that could suck air out of a container. He created what we now call a vacuum, a space with no air in it. This was revolutionary because it proved Aristotle wrong. You could create empty space. It was not impossible after all. Von Guericke did a famous demonstration to show how powerful a vacuum is. He took two large metal hemispheres and put them together to make a sphere. Then he pumped all the air out from inside. The two hemispheres were held together so tightly by the pressure of air pushing from outside that even teams of horses pulling in opposite directions could not pull them apart. This showed that air has real pressure and that removing air creates something different, a vacuum. This led to a crucial question that scientists are still debating today. When you remove all the air from a container, what is left? Is there truly nothing inside, or is there still something there that we just cannot detect? Isaac Newton, the genius who figured out gravity and the laws of motion, thought about this problem carefully. He concluded that space must be like an invisible, unchanging stage where the cosmic drama unfolds. Think of space as a giant theatre. The stage does not move, does not change, and does not care what happens on it. Actors come and go, props are moved around, but the stage itself just sits there, providing a background for everything else. That was Newton's picture of space. An absolute, unchanging, invisible grid that exists everywhere and always. Newton imagined that if you removed everything from a region of space, every particle, every bit of matter, every bit of energy, you would be left with pure, empty space. And that empty space would still have properties. It would still have 3 dimensions: left, right, forward, backward, and up, down. You could still measure distances in this empty space. 2 points separated by 1 meter would be 1 meter apart, whether anything existed between them or not. This idea seemed perfectly reasonable to Newton and to scientists for the next 200 years. It matched everyday experience. When you throw a ball, it moves through space. When planets orbit the sun, they move through space. Space is the container where all motion happens. It is the stage, and everything else is just performers on that stage. But there was a problem brewing on the horizon, a problem that would shatter this simple picture. And it all started with a simple question about light. Chapter 2. Newton's Stage. Let us explore Newton's worldview more carefully, because understanding what he believed will make Einstein's revolution even more shocking when we get there. In Newton's universe, space and time are completely separate things. Space is the three-dimensional stage where everything exists. Time is like a cosmic clock that ticks at the same rate everywhere in the universe. Imagine a giant clock hanging above the cosmic theatre, visible from every seat. That clock shows the absolute time, and everyone agrees on what time it is. Here is what this means practically. Imagine two twins are born at the exact same moment. One twin stays on Earth, and the other twin immediately gets on a spaceship and travels to a distant star at incredibly high speed. According to Newton, when the traveling twin returns to Earth after what feels like 10 years to them, they will find their Earth twin has also aged exactly 10 years. Time passes at the same rate for everyone, everywhere, always. There is an absolute universal now that everyone shares. Similarly, Newton believed in absolute space. This means there's a universal reference frame, a God's eye view of the universe where you can say absolutely whether something is moving or standing still. Imagine drawing an invisible grid throughout the entire universe. If an object stays at the same point on this grid, it is truly at rest. If it moves from one grid point to another, it is truly moving. The grid itself is absolute space. It does not move or change. Newton knew this was a bit strange because we cannot see this absolute space grid. We cannot grab onto it or measure it directly. But he thought it must exist because his laws of motion seem to require it. When you feel pushed backward in a car that accelerates forward, Newton said you are being pushed because you are accelerating relative to absolute space. Here is an example that shows how Newton's universe works. You are standing on the ground and you throw a ball forward at 20 meters per second. To you, the ball appears to move at 20 meters per second. Now imagine your friend is in a car driving toward you at 10 meters per second. From their perspective, how fast is the ball moving? It is moving 20 plus 10 = 30 meters per second toward them. Velocities ADD together in Newton's universe. This is called Galilean relativity, and it makes perfect intuitive sense. Everything in Newton's universe is like this, simple, intuitive, predictable. Space provides the background, time ticks away at a constant rate, and objects move through space as time passes. You can predict where everything will be at any future moment if you know where everything is now and what forces are acting. The universe is like a giant clockwork mechanism, and Newton had figured out the rules. For 200 years, this picture worked beautifully. Scientists used Newton's laws to predict the motion of planets with incredible accuracy. They discovered new planets like Neptune by calculating where it must be based on tiny wobbles in other planets' orbits. Engineers used Newton's laws to build bridges, design machines, and calculate trajectories. Everything worked. Everyone was happy. Newton's universe seemed complete and correct. Most scientists thought the big questions had been answered. Physics was done. We just needed to fill in some details. But they were wrong, spectacularly, magnificently wrong, because lurking in those details was a problem that would destroy Newton's entire worldview and replace it with something far stranger. That problem was light, and to understand it, we need to talk about waves. Chapter 3. The light problem. Think about the last time you threw a rock into a calm lake. You watched ripples spread out in perfect circles from where the rock hit the water. Those ripples are waves. Now bang on a drum and watch the drumhead vibrate. Those vibrations create waves in the air that travel to your ears. Sound waves. Waves are everywhere in nature. Ocean waves, sound waves, earthquake waves, waves on a slinky, they are all around us. Now, here is something crucial about waves. Every wave we had ever observed needed a medium to travel through. Water waves travel through water. Sound waves travel through air, or water, or metal, or any substance. Earthquake waves travel through the solid rock of Earth's crust. Without a medium, you cannot have a wave. This is why there is no sound in space. There is no air or anything else for sound waves to travel through. So when scientists in the 1800s figured out that light is a wave, they immediately had a problem. Light clearly travels through empty space. We can see the sun, which is 150 million kilometers away across the vacuum of space. Light from distant stars travels billions of years through the emptiness of space to reach our eyes. If light is a wave, what medium is it waving through? This was not just some abstract puzzle. This was a crisis for physics. James Clerk Maxwell had just figured out the mathematics of light in the 1860s. He proved that light is an electromagnetic wave, a wave made of oscillating electric and magnetic fields. His equations described light perfectly, but those equations seem to describe a wave, and waves need something to wave through. So scientists did what scientists always do when they have a problem. They invented a solution. They said, there must be an invisible, undetectable substance filling all of space, and light waves are ripples in that substance. They called this mystery substance the luminiferous ether, or just the ether for short. The word luminiferous literally means light-bearing. This was the stuff that supposedly carries light across the universe. But this ether had to have the most bizarre properties imaginable. Think about it. The ether had to be solid enough or stiff enough to allow light waves to propagate through it. Light moves fast, 300,000 kilometers per second, so the ether had to be incredibly rigid to support waves moving that fast. It would have to be stiffer than diamond. At the same time, the ether had to be so thin, so insubstantial, that planets could move through it without slowing down at all. Earth orbits the Sun at about 30 kilometers per second. The Sun itself is moving through the galaxy at 200 kilometers per second. If there was a thick ether filling space like molasses, Earth would have slowed down and crashed into the Sun billions of years ago. But Earth is still going strong, so the ether must create no resistance whatsoever. Does this sound impossible to you? It should, because it is impossible. You cannot have something that is rigid like diamond, but also thinner than air. But scientists were committed to this idea because they could not imagine waves without a medium. So they tried to figure out the properties of this mysterious ether. And here is where things get exciting. If the ether exists, we should be able to detect it. Here is why. Earth is moving through space at high speed as it orbits the Sun. If space is filled with stationary ether, then Earth is ploughing through this ether like a car drives through air. When you stick your hand out of a moving car window, you feel an air wind because you're moving through stationary air. Similarly, Earth should experience an ether wind because we are moving through stationary ether. This ether wind should have a measurable effect on light. Imagine swimming in a river. If you swim upstream, against the current, you move slower than if you swim downstream with the current. The current affects your speed. Similarly, light travelling against the ether wind should move slightly slower than light travelling with the ether wind, at least when measured by someone on Earth. In 1887, two American scientists named Albert Michelson and Edward Morley built an incredibly sensitive experiment to detect this ether wind. Their apparatus was called an interferometer, and it worked like this. They split a beam of light into two perpendicular beams, sent them down two paths at right angles to each other, bounced them off mirrors, and brought them back together. If one beam was travelling parallel to Earth's motion through the ether and the other was travelling perpendicular to it, the two beams should take slightly different amounts of time to make the trip. When the beams recombined, they would be slightly out of sync, creating an interference pattern. Michelson and Morley expected to see this interference pattern change as Earth moved through the ether. As Earth orbits the Sun, the direction of our motion through the ether should change, so the ether wind should come from different directions at different times of year. They did the experiment over and over at different times of day and different times of year, expecting to see the pattern shift as the ether wind changed direction. The result they got was shocking. Nothing. No ether wind. No difference in the speed of light in different directions. Zero effect. The interference pattern did not budge. It was as if the ether did not exist at all. This was one of the most important negative results in the history of science. They were not expecting it. They were not happy about it. Michelson himself was disappointed because he could not find what he was looking for. But this null result was screaming something profound. Either the ether does not exist, or something weird is going on with space and time that we do not understand. Scientists tried to save the ether theory with increasingly desperate ideas. Maybe Earth drags the ether along with it, so there is no relative motion. Maybe objects contract in the direction of motion through the ether in just the right way to hide the effect. These ad hoc explanations felt forced and ugly. Something was wrong with the whole picture. And then a 26-year-old patent clerk in Switzerland, who had read about the Michelson-Morley experiment, had a thought that would change everything. His name was Albert Einstein, and his idea was so simple yet so radical that it would destroy Newton's absolute space and absolute time, merge them into something new, and force us to completely reimagine what reality is. Chapter 4. Einstein's revolution. Begins in 1905, Albert Einstein was working in a patent office in Bern, Switzerland. He was not a professor. He was not at a famous university. He was just a young man evaluating patent applications during the day and thinking about physics at night. And in his spare time, he was having thoughts that would earn him a place among the greatest geniuses in human history. Einstein loved thought experiments, imaginary scenarios that help you think through the consequences of an idea. Here was his most famous one. Imagine you are running alongside a beam of light, trying to keep pace with it. If you could run at the speed of light, 300,000 kilometers per second, what would you see? According to common sense and Newton's physics, you should see the light wave frozen next to you, standing still like a sculpture made of light. Just like if you drive at 60 miles per hour next to a car, also going 60 miles per hour, that car appears stationary relative to you. The light wave should look stationary relative to you if you are moving at its speed. But Einstein realized this created a contradiction. Maxwell's equations, the laws that govern electricity, magnetism and light, do not allow for a stationary light wave. A frozen electromagnetic wave would violate the fundamental laws of electromagnetism. It cannot exist. So something is wrong with the reasoning. Einstein made a radical proposal. What if light always travels at the same speed, no matter how fast you are moving? What if the speed of light is constant for every observer, regardless of their motion? Let that sink in for a moment, because this is absolutely bizarre. Imagine you are standing still and someone shines a flashlight. You measure the light moving at 300,000 kilometers per second. Now imagine you are on a spaceship moving toward the flashlight at 99% the speed of light, moving at 297,000 kilometers per second. Common sense says you should measure the light approaching you at 300,000 plus 297,000 equals 597,000 kilometers per second. But Einstein said no. You measure the light moving at exactly 300,000 kilometers per second. The same speed, always the same speed. How is that possible? How can light have the same speed for everyone, regardless of how fast they are moving? There is only one way this can be true. Space and time themselves must be flexible. They must stretch and compress to keep the speed of light constant. Let me give you an analogy that helps make this less weird. Imagine you are trying to measure the speed of someone walking on a moving sidewalk at an airport. If the person walks at 3 miles per hour and the sidewalk moves at 2 miles per hour in the same direction, then relative to the ground, the person is moving at 5 miles per hour. That is normal addition of velocities. But now imagine a weird airport where the floor itself stretches or compresses to ensure that everyone always measures the walking person as moving at exactly 3 miles per hour, no matter how fast the sidewalk is moving. The floor would have to physically stretch out if the sidewalk moved forward, and compress if the sidewalk moved backward, all to make the walker's speed stay constant. That is what space and time do with light. Einstein worked out the mathematics of this idea, and the consequences were shocking. First consequence: time dilation. Time passes at different rates for people moving at different speeds. Imagine two twins. Twin A stays on Earth. Twin B gets on a spaceship and travels at 99% the speed of light for what seems to her like 1 year, then returns home. When she gets back, she finds that 10 years have passed on Earth. Her twin brother is now 9 years older than her. This is not science fiction. This is real physics, confirmed by countless experiments. Second consequence, length contraction. Objects moving at high speed get shorter in the direction of motion. If that spaceship is 100 meters long when sitting still, when it zooms past you at 99% the speed of light, you would measure it as only 14 meters long. The spaceship has been squished, but to the astronaut inside, everything seems normal. She measures the spaceship as still being 100 meters long, but she sees the rest of the universe compressed in the direction of motion. Third consequence, relativity of simultaneity. This is the weirdest one. Two events that happen at the same time for one observer might not happen at the same time for another observer moving relative to the first. The concept of a universal now that everyone agrees on does not exist. There is no absolute time. These predictions seemed insane when Einstein first proposed them. But here is the remarkable thing. Every single one has been confirmed by experiment. We have flown atomic clocks on airplanes and compared them to identical clocks left on the ground. The moving clocks ticked slower, exactly as Einstein predicted. We have accelerated particles to 99.99% the speed of light in particle accelerators. They live longer before decaying because time is passing slower for them. GPS satellites have to account for both time dilation effects, or your GPS would not work. Einstein called his theory special relativity. Special because it applies to the special case where there is no acceleration or gravity involved, just uniform motion. And the key insight was this: space and time are not separate. They are woven together into a four-dimensional fabric called space-time. Think about it this way. When you describe an event, say a car crash, you need 4 numbers. 3 numbers tell you where it happened, latitude, longitude and altitude, and 1 number tells you when it happened, the time. Einstein realized these 4 numbers are connected in ways Newton never imagined. Space and time can trade off with each other. When you move faster through space, you move slower through time. When you move slower through space, you move faster through time. They are like 2 sides of the same coin. Here is a helpful analogy. Imagine you are walking north across a field. If you turn slightly to the east, you are now moving less north and more east, but your total walking speed stays the same. In space-time, motion through time and motion through space trade off similarly. When you accelerate through space, you are turning in space-time, which means you move less through time and more through space. This was revolutionary. Newton's absolute space and absolute time were gone, destroyed, replaced by this weird unified thing called space-time, where different observers disagree about distances, time intervals, and even which events happen first. But all observers agree on the speed of light and on the laws of physics. And yet Einstein was not done. Special relativity was amazing, but it only applied to objects moving at constant speed. It did not include acceleration, and it did not include gravity. So Einstein spent the next 10 years working on an even more revolutionary idea. An idea that would answer the question we started with. What is space-time? Is it just a stage where things happen, or is it something? Something real that can be affected and shaped by matter and energy. The answer Einstein discovered was so beautiful and so strange that it changed not just physics, but our entire conception of reality. Chapter 5. Merging Space and Time. To truly understand what space-time is, we need to make this abstract concept feel real and concrete. So let us start with something totally familiar and build up from there. Imagine you are meeting a friend for coffee. You text them and say, "Let me meet you at Corner Cafe at 3 p.m. Notice what you just did. You specified 4 pieces of information. You said where to meet. Corner Cafe has a location. Let us say it is at the corner of 5th and Main. That location needs 3 numbers to specify completely. How far east or west, how far north or south, and what floor or altitude. Then you said when to meet, 3 p.m. That is the 4th number. 3 numbers for space, 1 number for time. In Newton's universe, these 4 numbers were completely independent. Space was space, time was time, and never the twain shall meet. But Einstein discovered they are intertwined in the most intimate way possible. Here is how we visualize this. Picture a simple graph. The horizontal axis represents position in space. Let us just use one dimension of space to keep it simple. The vertical axis represents time. Every point on this graph is an event, something happening at a particular place at a particular time. Your birth was an event. You reading this sentence right now is an event. Every moment of your existence is a series of events in space-time. Now draw a line on this graph showing where you are at every moment of time. If you are sitting still, the line goes straight up, same position, advancing through time. If you're moving, the line tilts to the side, changing position as time advances. This line is called your world line. It is the complete story of your journey through space-time. Every object in the universe has a world line. It is the path it traces through the 4-dimensional space-time. Here is where it gets interesting. In Newton's world, everyone agrees on how much space separates 2 events and how much time separates them. But in Einstein's world, different observers will disagree about these measurements. What does not change, what is absolute, is something called the space-time interval. It is a particular combination of the space and time separations that all observers agree on, even though they disagree on the space and time parts individually. This is shockingly similar to something totally familiar. Imagine you and a friend are both looking at the same building, but from different angles. You might say the building extends 50 meters to the north and 30 meters to the east. Your friend, looking from a different position, might say it extends 40 meters to the north and 40 meters to the east. You disagree about the north-south and east-west measurements, but you agree on the total distance from one corner to the opposite corner. That distance is absolute. It does not depend on your perspective. Space-time works the same way. The space part and the time part of an interval can be rotated between observers, mathematically speaking, but the space-time interval remains constant. This is the deep truth of special relativity. Space-time is a unified thing, and space and time are just different perspectives on that unified thing. Now, let us talk about the consequences we mentioned earlier, but in more depth. Time dilation is the fact that moving clocks tick slower. The faster you move through space, the slower you move through time. Think of it like this. You are always moving through space-time at a constant total speed, the speed of light, actually. If more of your motion goes into moving through space, less of it goes into moving through time. So your clock slows down. Here is a real example with real numbers. The GPS satellites orbiting Earth move at about 14,000 kilometers per hour. That is fast, but still only 0.001% the speed of light. Even at this tiny fraction of light speed, special relativity says the satellite clocks should tick about 7 microseconds per day, slower than clocks on the ground. And guess what? They do. We have measured this precisely. If we did not correct for it, GPS would drift by kilometers every single day. Length contraction is even weirder. Objects get shorter in the direction they are moving, but only from the perspective of someone watching them zoom by. Imagine a spaceship that is 100 meters long at rest. When it flies past you at 90% the speed of light, you would measure it as only about 44 meters long. It has been squished to less than half its length. But the astronauts inside feel nothing unusual. They still measure the spaceship as 100 meters long. However, when they look out the window, they see the rest of the universe compressed in the direction of motion. This is not an optical illusion. This is not the spaceship appearing shorter because of the time it takes light to travel. This is reality being different for different observers. Both perspectives are equally valid. You are right that the spaceship is 44 meters long in your reference frame. The astronauts are right that it is 100 meters long in their reference frame. This is what relativity means. Reality depends on your reference frame. Now, here is the consequence that really bends your mind. Relativity of simultaneity. Imagine two lightning bolts strike at opposite ends of a moving train. An observer standing on the ground, exactly midway between the strikes, sees them happen at exactly the same time. But an observer on the train, also midway between the strikes, sees the front lightning bolt strike before the rear one. Both observers are correct. There is no absolute answer to the question, did they happen at the same time? The answer depends on your motion. This destroys the idea of a universal now. You and I might disagree about whether two distant events happened at the same time, and we can both be right. The past, present, and future are not absolute categories. They are relative to the observer. Some philosophers say this means that, in a sense, all of time exists simultaneously from the perspective of space-time itself. Past, present, and future are all equally real. We just happen to be moving through time in a particular direction. The unity of space and time is complete. They are not separate entities. They are components of a single four-dimensional reality, space-time. Just as north-south and east-west are different directions in space, but both are equally spatial, time forward and space sideways are different directions in space-time, but both are equally real dimensions. This is the first great insight. Space-time is unified. But we still have not answered our question, what is it made of? Newton thought space was a stage. In special relativity, space-time is still a kind of stage. It is the arena where events happen, but it does not really do anything. It just sits there, providing the framework. But then Einstein had his second brilliant insight, and this one changed everything. He realized space-time is not just a stage. It is an active player in the cosmic drama. And the force that revealed this fact was gravity. Chapter 6. Gravity's Secret Identity. Let us talk about gravity for a moment. You have been experiencing gravity your entire life. It keeps your feet on the ground, it pulls a drop ball downward, it holds the moon in orbit around Earth and Earth in orbit around the sun. But what is gravity? Where does this force come from? Isaac Newton gave us an answer in 1687. He said, "Gravity is a force, an invisible pulling action that every mass exerts on every other mass. The Earth pulls on you, you pull on the Earth, the Sun pulls on all the planets, and so on." Newton even gave us a formula for calculating exactly how strong this force is. It is proportional to the product of the two masses and inversely proportional to the square of the distance between them. The formula works beautifully. We have used it to send spacecraft to every planet in the solar system. But Newton himself admitted there was something deeply mysterious about his theory. How does gravity work instantly across empty space? How does the Sun, which is 150 million kilometers away, know to pull on Earth? There is nothing between the Sun and Earth except empty space and some sparse gas and particles. How does the gravitational force travel across this emptiness? Newton famously said he would not speculate. He just knew the math worked. For over 200 years, nobody had a better answer. And then Einstein started thinking about it. The breakthrough came to Einstein in 1907, and it started with what he later called the happiest thought of my life. He imagined a person falling off a roof. Now, this might not seem like a happy thought, but bear with me. Einstein realized something profound. While you are falling, you do not feel gravity. You feel weightless. Think about this carefully. Imagine you are in an elevator and the cable snaps. As you plummet downward, you would not feel like you are being pulled down. You would feel like you are floating. If you let go of your phone, it would not fall relative to you. It would float in mid-air next to you because it is falling at the same rate you are. Inside that falling elevator for those terrifying seconds, you would experience weightlessness, just like astronauts in space. Einstein realized this is not a coincidence. Falling freely and floating in space, far from any gravity, are physically identical experiences. There is no experiment you could do inside a closed box to tell whether you are falling freely on Earth or floating in deep space far from any mass. None. This is called the equivalence principle. Now flip it around. Imagine you are in a closed box sitting on the ground on Earth. You feel weight, your feet press against the floor. But Einstein realized this is also indistinguishable from another situation. Being in a box out in space that is accelerating upward at 9.8 meters per second squared, which is the same rate that objects fall on Earth. The floor of the box pushes up on your feet with exactly the same force in both cases. Here is Einstein's stunning conclusion. Gravity is not a force. What you call gravity is actually the absence of force. When you're in free fall, no forces act on you. You're moving naturally through space-time. When you're standing on the ground is pushing up on you, preventing you from moving naturally through space-time. But if gravity is not a force, what is it? Einstein's answer was revolutionary. Gravity is the curvature of space-time itself. Let me explain with the analogy everyone uses because it is genuinely helpful. Picture a stretched rubber sheet, like a trampoline. This sheet represents space in 2 dimensions for visualization. Place a heavy bowling ball in the center. The sheet de-eyepiece down, creating a curved surface around the ball. Now roll a marble across the sheet. What happens? The marble does not roll in a straight line. It curves toward the bowling ball, not because the bowling ball is exerting a force on it, but because the surface itself is curved. The marble is following the straightest possible path, a geodesic on a curved surface. This is what mass does to space-time. The sun's mass curves space-time around it, creating a dip. Earth is not being pulled toward the sun. Earth is moving in the straightest possible path through curved space-time. That path happens to be an ellipse because of the curvature. Earth is essentially rolling around the dip in space-time created by the sun. Now I need to warn you, the trampoline analogy has a weakness. It makes it look like the sun creates a dip downward in space, as if there is a gravitational force pulling the trampoline down. But that is not what is happening. Space-time does not curve into anything. It curves intrinsically. The geometry itself changes. Here is a better way to think about it. Imagine you are an ant walking on the surface of a sphere, like Earth. The surface is curved, but you're not curving through some higher dimension. The surface itself has a curved geometry. Parallel lines converge like longitude lines meeting at the poles, and the angles inside a triangle do not add up to 180 degrees. That is intrinsic curvature. The curvature exists within the surface itself, not as a bending through a higher dimension. Space-time works the same way. Mass and energy curve space-time, and this curvature exists in the fabric of space-time itself. You do not need a higher dimension for it to curve into. Here is what this solves. Newton's mystery of how gravity works instantly across space disappears. Gravity does not have to travel across space because it is the shape of space. The sun curves the space-time around it, and Earth simply moves through that curved space-time. Changes in the curvature propagate at the speed of light as gravitational waves, but there is no mysterious action at a distance. Einstein published this idea in 1915 as his theory of general relativity. The equations are complex, but the core idea is beautifully simple. Matter tells space-time how to curve, and curved space-time tells matter how to move. This changes everything about how we think about space-time. Space-time is not just a passive stage. It is dynamic. It responds to matter and energy. It can bend, stretch, compress and wave. It is a physical thing with properties, even though we cannot see it or touch it directly. And this is where we get closer to answering our original question. What is space-time made of? If it can curve and wave like a physical material, surely it must be something, right? Let us explore what this curvature means. Chapter 7. The Fabric Metaphor. We keep calling it the fabric of space-time. This metaphor appears everywhere in popular science. You have probably heard it countless times. But let us pause and think carefully about this metaphor, because it is both helpful and misleading. First, what does the metaphor get right? Fabric is something you can manipulate. You can stretch it, compress it, bend it, twist it, even tear it if you pull hard enough. All of these things can happen to space-time according to general relativity. Space-time can stretch, the universe is expanding, compress near massive objects, bend, gravitational lensing, and possibly even tear at singularities inside black holes. Fabric also connects things. When you pull one part of a piece of cloth, other parts move too. Similarly, space-time connects all events in the universe. What happens at one point in space-time can influence what happens at nearby points. This connectedness is real and important. Fabric can also wave. If you shake one end of a bedsheet, waves ripple across it. Similarly, space-time can support waves, gravitational waves that travel at the speed of light, carrying energy across the universe. But here is what the metaphor misses, and this is crucial. Fabric is made of threads. Those threads are woven together from fibers. Those fibers are made of long-chain molecules. Those molecules are made of atoms. Fabric has structure all the way down. So, when we call space-time a fabric, the obvious question is, what are the threads? What are the atoms of space-time? Is there some tiny fundamental unit that space-time is built from, like bricks building a wall? Einstein himself did not think so. To Einstein, space-time was fundamental. It was not made of anything smaller. Space-time was pure geometry. Asking what space-time is made of was, to Einstein, like asking what the number 7 is made of. Numbers are not made of anything. They are fundamental mathematical objects. Similarly, Einstein thought space-time was just the geometric structure of reality. It was the thing that everything else exists in. In Einstein's view, when we say space-time curves, we mean the geometry changes. The distance between points changes. The angles inside triangles change. These are mathematical facts about the structure of space-time, not facts about tiny components moving around. But modern physicists are not so sure. Many of them suspect that space-time does have a substructure, a deeper level of reality that becomes important at extremely small scales. They think space-time might be emergent, like how water emerges from molecules. Think about water for a moment. When you pour water from a cup, it flows smoothly and continuously. It seems like a perfectly smooth substance. But we know water is made of individual H2O molecules. Zoom in far enough and the smooth flow disappears. You see discrete molecules bouncing around. The smooth, continuous nature of water is an illusion that only appears when you look at trillions of molecules together. Could space-time be the same way? Could it seem smooth and continuous at the scales we can measure, but actually be made of tiny discrete units, at scales far smaller than we can probe? Many physicists think yes. Here is why this question matters. In quantum mechanics, everything is ultimately quantized. It comes in discrete chunks. Energy comes in quanta, photons. Angular momentum comes in discrete units. Even electromagnetic fields are quantized. If space-time is truly a physical thing and not just abstract geometry, then maybe it should be quantized too. Maybe there is a smallest possible unit of space and a smallest possible unit of time. This is where the metaphor gets stretched to its breaking point. If space-time is truly like a fabric with threads, then those threads must be quantum threads. And quantum threads behave nothing like classical threads. They would be governed by uncertainty principles, quantum fluctuations, and all the weirdness of the quantum world. Some physicists imagine that at the smallest scales, far smaller than atoms, smaller than protons, smaller than anything we can possibly measure, space-time is not smooth at all. It is foaming and bubbling with quantum uncertainty. This is called quantum foam, and we will explore it more later. For now, just understand that the smooth space-time we experience might be like the smooth surface of the ocean. Look at it from an airplane, and it appears perfectly smooth. Get up close, and you see waves, ripples, and turbulence. Get really close, and you see individual water molecules chaotically bouncing around. Is space-time like that? Is there a deeper structure we cannot see yet? To answer these questions, we need to do something dramatic. We need to watch space-time do something that reveals its nature. We need to see it. Wave. Chapter 8. When Space-Time Waves. In 1916, just 1 year after publishing General Relativity, Einstein realized his equations predicted something absolutely wild. If space-time can curve, then it should also be able to ripple. Just like if a drumhead can be pushed down, it can also vibrate and create sound waves. Space-time should be able to support waves that travel across the universe. Einstein called these hypothetical waves gravitational waves. Imagine throwing a stone into a perfectly still pond. The stone creates ripples that spread out in circles. These ripples are waves in the water surface. The height of the water oscillates up and down as the wave passes. Gravitational waves are similar, except they are ripples in space-time itself. As a gravitational wave passes through you, space itself alternately stretches and squeezes. What could create such waves? Einstein realized that any accelerating mass creates gravitational waves, but the effect is usually fantastically small. If you wave your arms, you create gravitational waves, but they are so weak that they are utterly impossible to detect. To create gravitational waves strong enough to detect, you need something enormous and violent, like two black holes spinning around each other at a significant fraction of the speed of light. Imagine two black holes, each containing the mass of many suns, orbiting each other. They are locked in a death spiral, getting closer and closer. As they orbit, they shake space-time violently, like two massive weights spinning on opposite ends of a jump rope. This shaking creates gravitational waves that propagate outward at the speed of light, spreading across the entire universe. Here is what is mind-blowing. These waves literally stretch and squeeze space as they pass. Imagine a gravitational wave passing through you from left to right. As the wave passes, space stretches in the up-down direction and compresses in the left-right direction, then reverses. You would be alternately stretched vertically and compressed horizontally, then stretched horizontally and compressed vertically, oscillating back and forth. But the effect is absurdly tiny. A gravitational wave from two black holes colliding billions of light-years away would stretch space by about 1 part in 10 to the 21. To put that in perspective, if you had a stick 4 kilometers long, the distance from New York to New Jersey through the Lincoln Tunnel, the gravitational wave would stretch it by less than the width of a proton. That is 1/10,000th the size of an atom. For decades, gravitational waves remained purely theoretical. Einstein himself doubted we would ever detect them because the effect is so small. But scientists are stubborn and creative. In the 1970s and 1980s, physicists began building gravitational wave detectors called LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO works like this. You build two arms, each 4 kilometers long, arranged in an L shape. You shine a laser beam down each arm, bounce it off a mirror at the far end, and bring the beams back together. If a gravitational wave passes through, one arm gets slightly longer while the other gets slightly shorter. This creates a tiny timing difference in when the laser beams return, which shows up as an interference pattern. But remember, the effect is smaller than a proton across 4 kilometers. To detect this, LIGO had to be the most sensitive scientific instrument ever built. The mirrors had to be isolated from every possible vibration. Earthquakes, traffic, ocean waves, even random thermal jostling of atoms. It was an incredible engineering challenge. For years, LIGO ran and detected nothing. Many physicists started to wonder if Einstein had been right. Maybe gravitational waves could never be detected. But the team kept improving the detector, making it more and more sensitive. And then, on September 14, 2015, both LIGO detectors, there is one in Louisiana and one in Washington State, simultaneously detected a signal. The signal was perfect. It matched Einstein's predictions exactly. Two black holes, one containing 36 times the Sun's mass and the other 29 times the Sun's mass, had spiraled together 1.3 billion light-years away. As they orbited faster and faster, they emitted gravitational waves with increasing frequency and amplitude, a pattern that sounded like a chirp when converted to sound. In the final moments before collision, the black holes were orbiting each other hundreds of times per second. When they finally merged, they released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. Think about that. For a brief instant, this collision outshone the entire universe, not in light, but in gravitational waves. And here is what this detection proves about space-time. Space-time is real. It is not just a mathematical abstraction. It is a physical thing that can wave, vibrate, and carry energy. When those gravitational waves passed through Earth, they literally stretched and squeezed space itself. The ground beneath your feet, the air around you, even your body. Everything expanded and contracted slightly as the wave passed through. This is profound. Space-time has properties. It has something like stiffness or rigidity that allows it to support waves. When you pluck a guitar string, it vibrates because it has tension. When you tap a drum, it vibrates because the membrane has elasticity. Space-time can vibrate, which means it has physical properties similar to these materials. So space-time is not nothing. It is something. It is a medium that can transmit waves. It has a structure, even if we cannot see or touch it directly. This brings us back to our central question with renewed urgency. If space-time has physical properties like a material, what is it made of? What gives it these properties? To answer this question, we need to zoom in. Way in. We need to look at space-time at the smallest possible scales. And when we do that, we enter a realm where Einstein's smooth curved space-time meets another theory, quantum mechanics. And these two theories do not play nicely together. Chapter 9. Welcome to the quantum world. While Einstein was revolutionizing our understanding of space, time, and gravity, the physics of the very large, other scientists were discovering something equally strange in the very small. In the early 1900s, physicists began probing inside atoms, and what they found was so weird that it forced them to completely rethink the nature of reality. Let me introduce you to the quantum world by showing you just how different it is from everyday experience. In our normal world, the world of coffee cups and basketballs and planets, objects have definite positions and velocities. A ball is here or there. It is moving at this speed or that speed, simple, clear, definite. But in the quantum world, nothing is definite until you measure it. Here is what I mean. Take an electron. If you do not measure where it is, it does not have a definite position. It exists in a fuzzy cloud of probability. It might be here, might be there, might be over there. It is not that we do not know where it is. It is that it literally does not have a definite position until you measure it. When you finally measure the electron's position, the probability cloud collapses and the electron appears at one specific location. This is not a limitation of our measuring equipment. This is fundamental to reality. Particles in the quantum world are inherently uncertain. Werner Heisenberg proved this with his famous uncertainty principle. You cannot know both the position and the momentum, mass times velocity, of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. Not because of measurement errors, but because the particle simply does not have exact values for both quantities simultaneously. But it gets weirder. Particles are not just particles, they are also waves. This is called wave-particle duality. An electron can behave like a tiny solid ball, or it can behave like a wave spread out in space. Which behavior you see depends on how you measure it. Shine electrons through two narrow slits, and they create an interference pattern on a screen behind the slits, just like water waves do. Each electron somehow interferes with itself, as if it went through both slits simultaneously. And here is the kicker. If you try to observe which slit the electron goes through, the interference pattern disappears. The electron starts behaving like a particle instead of a wave. The act of observation changes the behavior. This is not because measuring devices are clumsy. It is because at the quantum level, observation is an interaction that fundamentally affects what is being observed. Let me give you one more piece of quantum weirdness that will be important later. Quantization. In the quantum world, many things come in discrete chunks, not continuous values. Energy, for example, does not come in arbitrary amounts. It comes in specific units called quanta. When an electron orbits an atom, it can only occupy certain specific energy levels. It cannot exist at intermediate energies. It must jump from one allowed level to another, releasing or absorbing a photon, a quantum of light, in the process. Think of it like a staircase versus a ramp. On a ramp, you can stand at any height, 2.5 meters, 2,501 meters, 2,000, 5,001 meters, any value you want. But on a staircase, you can only stand on discrete steps. You can be on step 2 or step 3, but you cannot stand at step 2.5. The quantum world is like a staircase. Many properties come in discrete quantized steps. Now here is why all of this matters for our question about space-time. Quantum mechanics has been spectacularly successful. It explains chemistry, the behavior of materials, electricity, magnetism, nuclear reactions, and every fundamental particle interaction. Every prediction of quantum mechanics that we have tested has been confirmed with incredible precision. It is probably the most successful scientific theory ever created. And yet, quantum mechanics and general relativity, Einstein's theory of gravity and curved space-time, contradict each other. They give different answers at extreme scales. They are based on fundamentally incompatible assumptions. General relativity treats space-time as smooth and continuous. Quantum mechanics suggests everything should be grainy and uncertain at small scales. They both cannot be completely correct. This is the biggest problem in fundamental physics. We have two theories, both incredibly successful in their own domains, but they do not fit together. And the only way to solve this problem is to develop a quantum theory of gravity, a theory that describes what space-time is like at quantum scales. And that will finally tell us what space-time is made of. But before we tackle that challenge, we need to understand one more crucial concept from quantum physics. Fields. Chapter 10. Fields, the universe's true building blocks. I need to tell you something that might shock you. Everything you think is a particle. Electrons, photons, quarks, even the exotic particles like the Higgs boson, are not really particles at all. They are vibrations in invisible fields that fill all of space. This idea is called quantum field theory, and understanding it is crucial to understanding what space-time might be made of. Let me start with a familiar example of a field that is not quantum. Think about temperature. On a hot summer day, the temperature in your room is not the same everywhere. It might be hotter near the window where sunlight streams in and cooler in the shadowy corner. Temperature is a field. It has a value at every point in space. You can make a temperature map showing the temperature at every location. That map is a visualization of the temperature field. Here is another example, a magnetic field. Place a bar magnet under a piece of paper and sprinkle iron filings on top. The filings align in beautiful curves, showing the magnetic field pattern. The field has a value and a direction at every point in space around the magnet. The field is real. It can push and pull on magnetic objects even though you cannot see it directly. Now comes the quantum revolution in thinking about fields. In the early 20th century, physicists realized that all particles are actually excitations, vibrations in quantum fields. There is an electron field filling all of space. When that field vibrates in a particular way, we observe an electron particle. There is a photon field, also called the electromagnetic field, and vibrations in that field appear to us as photons, particles of light. Think of it like the surface of a pond. The pond is the field. Ripples and waves on the pond are particles. A single ripple is like a single photon. A big wave is like many photons. The ripples move across the surface. They can collide and interact. They can merge or split apart, just like particles. But fundamentally, they are all just vibrations of the underlying pond. Here is the beautiful part. This explains wave-particle duality. An electron is not sometimes a wave and sometimes a particle. It is always a wave in the electron field. When we observe it in certain ways, it appears localized like a particle. When we observe it in other ways, we see its wave nature more clearly. But it is always fundamentally a field vibration. Every type of particle has its own field. There is a quark field for each type of quark, up quarks, down quarks, etc. There is a neutrino field. There is a Higgs field, the field whose vibrations are the famous Higgs boson particle. All of these fields overlap in the same space, occupying the same points, but they are independent fields that can vibrate separately. The universe is not empty space with particles moving through it. The universe is a collection of fields filling all space, and what we call particles are just localized vibrations in these fields. Space is more like an invisible ocean full of overlapping fields, and matter is like waves and ripples on those fields. Now here is the key question that brings us back to space-time. Is space-time itself a field? Or is space-time the stage on which fields perform, In Einstein's general relativity, spacetime seems to be the stage. Fields exist in spacetime. The electron field has a value at each point of spacetime. The photon field has a value at each point of spacetime. Spacetime is the background, the coordinates, the framework that holds everything else. But maybe that is wrong. Maybe spacetime itself is also a field, just like the electron field and the photon field. Maybe what we call space and time are just properties of some deeper quantum field, a gravitational field that fills reality. And maybe the curvature of space-time that Einstein discovered is actually just the way this quantum gravitational field vibrates and oscillates. If that is true, then asking what is space-time made of is like asking what is the electron field made of? And the answer might be it is made of quantum excitations, tiny vibrations at the deepest level of reality. But here is the problem. When physicists try to apply quantum mechanics to gravity to treat space-time as a quantum field, the math breaks. The equations give infinite answers that make no sense. This is not just a minor technical problem. It is a fundamental incompatibility, and it has stumped physicists for almost 100 years. To understand why gravity and quantum mechanics do not get along, we need to explore what happens at the smallest possible scales of space-time. Chapter 11. The quantum foam. Imagine you are shrinking. You start at your normal size, about 2 meters tall. Now shrink by a factor of 1,000. You are now 2 millimeters tall, the size of a small ant. Shrink again by 1,000. You are now 2 micrometers, about the size of a bacterium. Shrink again, now you are 2 nanometers, the size of a DNA molecule. Keep going. Shrink past the size of atoms, past the size of atomic nuclei, past the size of protons. How far can you shrink? Is there a limit? According to our current understanding, yes. There is a smallest meaningful size in physics called the Planck length. It is about 10 to the power of negative 35 meters. That is 1 times 10 to the power of negative 36 meters. To give you perspective, an atom is to this length as the entire observable universe is to an atom. The Planck length is absurdly, incomprehensibly tiny. At the Planck scale, something dramatic happens. The smooth, continuous space-time of Einstein's theory starts to break down. Quantum uncertainty becomes so extreme that space-time itself starts to fluctuate wildly. Physicist John Wheeler described this as quantum foam, a seething, frothing chaos at the deepest level of reality. Here is why this happens. Remember Heisenberg's uncertainty principle? It says you cannot know both the position and momentum of a particle with perfect precision. But there is another version of the uncertainty principle that involves energy and time. The more precisely you want to know the energy of something, the more time you need to measure it. Or flip it around. Over short enough time intervals, energy can fluctuate wildly and unpredictably. At everyday scales, these energy fluctuations are tiny and unmeasurable. But at the Planck scale, over time intervals of about 10 to the power of negative 43 seconds, the energy fluctuations become enormous. They are so large that they can spontaneously create particle-antiparticle pairs that pop into existence and then annihilate each other almost immediately. These are called virtual particles. But energy and mass are related by Einstein's famous equation E=mc2 and mass curves space-time. So these quantum energy fluctuations also create fluctuations in the curvature of space-time itself. At the Planck scale, space-time is not smooth. It is churning and boiling like water in a violently boiling pot. Wheeler imagined that at these scales, the geometry of space-time fluctuates wildly. Tiny wormholes might constantly form and dissolve. The number of dimensions might fluctuate. Maybe there are briefly 4 dimensions here, 5 dimensions there, 3 dimensions elsewhere. The topology itself, the basic structure of how space connects to itself, might be in constant flux. This quantum foam would be completely invisible to us because it exists at scales so small that we cannot possibly observe it directly. It is like looking at the ocean from an airplane. It appears perfectly smooth and blue, even though up close it is full of waves, ripples, and individual water molecules in chaotic motion. Some physicists believe that space-time at the Planck scale is not just fuzzy. It might be discrete, broken up into tiny chunks. Just as matter is made of atoms, space-time might be made of atoms of space-time. Tiny, indivisible units that cannot be subdivided further. Space would not be continuous like a smooth ramp, but quantized like a staircase made of extremely tiny steps. If this is true, then asking, what is space-time made of, has a concrete answer. Space-time is made of Planck-scale quantum bits of geometry, tiny grains of space that combine to create the smooth space-time we experience, just as grains of sand combine to create a smooth beach. But here is the profound problem. We have no direct evidence for any of this. The Planck scale is so fantastically small that we cannot probe it with experiments. Our most powerful particle accelerators can smash particles together at energies far below what would be needed to see Planck scale effects. It would take an accelerator larger than the entire galaxy to reach Planck scale energies. So the quantum foam remains hypothetical, a compelling idea based on combining quantum mechanics and gravity, but not yet proven. To make progress, physicists need a complete mathematical theory that correctly describes quantum gravity. And that is where the real struggle begins. Chapter 12, The Clash, Relativity versus Quantum Mechanics. Let me lay out the problem clearly because this is the heart of why we do not yet know what space-time is made of. We have 2 incredibly successful theories of physics, general relativity and quantum mechanics. Each works perfectly in its own domain, but they are fundamentally incompatible with each other. General relativity says space-time is smooth and continuous. You can zoom in infinitely far and space-time remains smooth. It curves gracefully in response to matter and energy. The geometry can be calculated precisely using Einstein's elegant equations. In general relativity, space-time is deterministic. If you know the current state of the universe, you can predict the future exactly. Quantum mechanics says everything is uncertain and probabilistic. You cannot know exact values for properties like position and momentum simultaneously. Everything comes in discrete quanta, chunks. The universe is fundamentally random at small scales. You can only predict probabilities, not certainties. And crucially, quantum mechanics requires fields and particles to be quantized, to come in discrete packets. These are not just different descriptions, they are contradictory worldviews. And when you try to apply both to the same situation, the math explodes into nonsense. Let me give you a concrete example: black holes. According to general relativity, if you compress enough mass into a small enough region, space-time curves so extremely that it creates a black hole. At the very center is a singularity, a point where the curvature becomes infinite. Density becomes infinite. Space-time itself breaks down. But infinity is not a real answer in physics. When your equations give you infinity, it means the theory has broken down. You are asking it a question it cannot answer. At the singularity, we need quantum mechanics to tell us what really happens. But general relativity is not a quantum theory, so it cannot describe the singularity properly. Similarly, at the moment of the Big Bang, all matter and energy in the universe was compressed into an infinitely small, infinitely dense point, another singularity. What really happened at T0, the very beginning? General relativity says singularity, which is just code for I don't know. Quantum mechanics should have the answer, but quantum mechanics does not include gravity, so it cannot describe the early universe when gravity was dominant. Here is another problem. When physicists try to quantize general relativity, apply the standard methods of quantum mechanics to Einstein's equations, they get nonsense. Specifically, they get infinite probabilities for certain processes. In normal quantum field theory, there are mathematical techniques called renormalization that can deal with certain infinities, but in quantum gravity, these techniques do not work. The infinities are non-renormalizable. They cannot be removed. Why does this happen? The root cause is that general relativity has curvature as its fundamental property. And curvature involves second derivatives, rates of change of rates of change. When you quantize this, you get quantum fluctuations at all possible energy scales, including infinitely high energies. These high-energy fluctuations create infinite contributions that ruin all your calculations. In contrast, quantum field theories for other forces work fine. Quantum electrodynamics, QED, the quantum theory of electricity and magnetism, gives predictions that match experiments to 10 decimal places. The quantum theories of the weak and strong nuclear forces also work beautifully. But gravity resists quantization. Here is yet another problem. In quantum mechanics, time is treated as a background parameter, a variable that ticks along smoothly while quantum states evolve. But in general relativity, time is part of space-time, and space-time is dynamic. Time can run at different rates in different places. Time does not exist as an absolute background. So how do you do quantum mechanics when time itself is fuzzy and uncertain? These are not small technical details. These are fundamental conceptual problems. For nearly a century, physicists have struggled with this. Legends like Einstein, Bohr, Heisenberg, Feynman and Hawking all wrestled with quantum gravity. Some made progress on specific aspects, but no one found a complete solution. This is why we do not know what space-time is made of. To answer that question, we need a quantum theory of gravity, a theory that correctly describes space-time at the smallest scales where quantum effects dominate. And we need this theory to reduce to Einstein's general relativity at large scales, which we know works, and to quantum mechanics at small scales, which we also know works. Finding this theory has been called the Holy Grail of theoretical physics, and many brilliant minds have tried. Let us look at their attempts. Chapter 13. Attempts at quantum gravity. Before we dive into the leading candidates for a quantum theory of gravity, let me quickly mention some earlier attempts that did not quite work out, but taught us valuable lessons. The first approach was to try the obvious thing. Apply the standard quantization methods used for other forces to gravity. This is called canonical quantum gravity, or sometimes quantum geometrodynamics. The idea is to take Einstein's equations, which describe how space-time geometry evolves, and apply quantum mechanics to them directly. The problem? The math becomes horrendously complicated. Einstein's equations are already among the most complex in physics, with 10 interrelated equations involving derivatives and geometric terms. When you try to quantize them, you get equations that are almost impossible to solve. Physicists made some progress. They found ways to describe quantum states of space geometry, but they could not extract useful predictions from the theory. The second approach is called quantum field theory in curved space-time. This is a halfway house, a compromise. Instead of trying to quantize gravity itself, you keep space-time classical, described by general relativity, but treat matter as quantum. So you have quantum particles moving through a curved classical space-time. This approach actually works pretty well for certain problems. It was used to predict that black holes should emit Hawking radiation, a quantum effect where black holes slowly evaporate. This was a major breakthrough, but it is not a complete theory of quantum gravity because it does not make space-time itself quantum. The third approach is called asymptotic safety. The idea here is that maybe gravity can be quantized using standard methods, and the infinities that appear are just an artifact of our approximation schemes. Maybe if you do the calculation more carefully, including all possible quantum corrections, the theory becomes well behaved at a fixed point where the infinities cancel out. This is still an active area of research, and some physicists think it might work. But it is difficult to prove whether this fixed point really exists, and most of the physics community has moved toward other approaches. There are also more exotic ideas. Causal dynamical triangulations, building space-time from gluing together simple geometric pieces. Non-commutative geometry, space where position coordinates do not commute mathematically, and various others. Each has interesting features, but none has achieved the level of development and support that the two leading candidates have. Those two leading candidates are string theory and loop quantum gravity. These are the approaches that have attracted the most attention, generated the most publications, and made the most progress toward a complete quantum theory of gravity. They take very different philosophical approaches and give very different answers to the question, what is space-time made of? String theory says, space-time is not fundamental. It emerges from the interactions of tiny vibrating strings. The threads of space-time, if you want to use that metaphor, are strings of energy. Loop quantum gravity says, space-time is fundamental, and it is made of something. Quantum loops of gravitational field woven together like a fabric. The threads of space-time are literal geometric threads. Let us explore both of these beautiful mind-bending theories. We will start with string theory, because chronologically it came first, and it is probably the one you've heard more about. Chapter 14. The String Theory Revolution. Imagine you are looking at an object from very far away, so far that you cannot see any details. A person looks like a dot. A car looks like a dot. Everything looks like a zero-dimensional point. Now zoom in closer. The person reveals structure. Arms, legs, a head. They are three-dimensional. Zoom in even more, down to the molecular level, then the atomic level, then inside the atom. Eventually you reach fundamental particles, electrons, quarks, photons. In standard physics, these particles are treated as point particles, zero-dimensional dots with no internal structure. An electron, as far as we can tell, has no size. It is infinitely small. This seems fine until you try to do quantum field theory with gravity, and then the infinities show up because you are dealing with objects of literally zero size. In the early 1970s, physicists working on the strong nuclear force stumbled onto a strange mathematical result. Their equations made more sense if they thought of particles not as points, but as tiny, vibrating strings. These strings would be incredibly small, about 35 meters long, the Planck length. At normal scales, even inside atoms, these strings would look exactly like point particles. But they would have structure, which might help with the infinity problems. At first, this string theory did not work for the strong force. It made wrong predictions. The theory seemed dead. But then, in 1974, physicists realized something amazing. String theory automatically includes gravity. One of the vibration patterns of a string naturally corresponded to the graviton, the hypothetical quantum particle of gravity. String theory was not just a theory of particles, it was a quantum theory of everything, including gravity. This was huge. Remember, the main problem with quantum gravity is that every attempt to quantize Einstein's theory led to infinities. But string theory avoided those infinities naturally. The extended structure of strings, they have length, not just position, smoothed out the infinities. It was the first mathematically consistent quantum theory that included gravity. So how does string theory work? Imagine the tiniest possible guitar string, but it is not attached to anything. It is floating in space. This string can vibrate in different patterns, like a guitar string can play different notes. Each vibration pattern corresponds to a different particle we observe. One pattern, an electron; another pattern, a quark; another, a photon; another, a graviton, the quantum of gravity. Different notes, different particles. All particles in the universe, all the building blocks of matter and all the force-carrying particles are just different vibrations of the same fundamental string. This is beautiful unification. One fundamental object explains everything. The strings can be open, like a line segment with two ends, or closed, like a tiny loop. They can vibrate, stretch, split apart, and join together. When strings interact, when two strings come close and join into one, or one string splits into two, this appears to us as particles interacting. A chemical reaction, a radioactive decay, light hitting your eye, all are ultimately strings interacting. Now, here is the crucial part for our question about space-time. In string theory, space-time is not fundamental. The strings are fundamental. Space-time emerges from the relationships and interactions between strings. It is like asking, what is a song made of? Fundamentally, a song is made of sound waves vibrating air molecules. But the song itself, the melody, the rhythm, the harmony, emerges from the relationships between those sound waves. Similarly, space and time emerge from the collective behavior of countless strings. Distance is a measure of how strings interact. Time is related to how string configurations evolve. The smooth space-time we experience is a large-scale collective phenomenon that emerges from quantum string dynamics, just like the smooth flow of water emerges from molecular interactions. But string theory comes with a price, a strange, beautiful, and controversial price. And it is this: string theory requires more dimensions than the four we experience, 3 space, 1 time. Let me explain. Chapter 15. Extra dimensions. When physicists first worked out the math of string theory, they ran into a problem. The equations only remained consistent and free of contradictions, if space has not 3 dimensions, but 9 spatial dimensions. Plus, time makes 10 total dimensions. Now, this might sound ridiculous. You can move left-right, forward-backward, and up-down. That is 3 dimensions of space. Where are the other 6 spatial dimensions? Do they not exist? Did physicists just make them up? Actually, the idea of hidden dimensions is not as crazy as it sounds. Let me give you an analogy that makes this intuitive. Imagine you are an ant crawling on a long, thin wire stretched across a room. From your ant perspective, you can only move in one dimension, forward or backward along the wire. But wait, you are an ant, not a point. You could also walk around the wire. There is a second dimension curled up in a tiny circle around the wire. From far away, from a human perspective, the wire looks one-dimensional. But up close, an ant discovers there is a hidden dimension curled up so small that it is hard to notice unless you are tiny. This is called a compact dimension, a dimension curled up into a small shape. This idea was actually first proposed in the 1920s by mathematicians Theodore Kaluza and Oscar Klein, decades before string theory. They wondered if our three-dimensional space might actually have a fourth spatial dimension curled up so small we cannot perceive it. They called this extra dimension the Kaluza-Klein dimension. String theory takes this idea and runs with it. Not just one extra dimension, but 6 extra dimensions, all curled up into complex geometric shapes smaller than an atom, so small we cannot detect them even with our most powerful microscopes or particle accelerators. But they cannot be curled up in just any shape. The math of string theory requires them to be curled up into very specific geometric structures called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xingtung Yau. These are 6-dimensional shapes with beautiful mathematical properties. They are compact, closed and finite, and they have a property called Ricci flatness that satisfies the equations. Now, you cannot visualize a 6-dimensional Calabi-Yau manifold directly. Our brains cannot picture 6 dimensions. But mathematicians can describe them with equations and create 2D or 3D projections that give a flavor of their structure. These projections look like intricate, flowing, organic shapes, like abstract sculptures or alien flowers. Here is why this matters. The exact shape of the compactified dimensions determines which particles and forces appear in our observable 3-dimensional world. Different Calabi-Yau shapes give different physics. The way the strings wrap around and vibrate through these extra dimensions determines what particle properties we measure: mass, charge, spin, and so on. This is both beautiful and problematic. Beautiful because it explains why particles have the properties they do. It is all about geometry in hidden dimensions. Problematic because there are many possible Calabi-Yau shapes, possibly 10 to the power 500s or more. Each one gives a different universe with different physics. Which one describes our universe? Nobody knows. But let us get back to our main question. What is space-time made of in string theory? The answer is now clearer. The 3 large spatial dimensions we experience, plus the 6 tiny compact dimensions, plus time, all 10 dimensions together, emerge from string interactions. Space-time is not made of stuff in the traditional sense. It is made of relationships between strings. Think of it like this. When strings interact, they exchange information about their states. This exchange creates a network of relationships. String A is related to string B in a certain way, B is related to C, and so on. The geometry of space-time is encoded in this network of relationships. Distance between 2 points is really a measure of how much interaction data needs to be exchanged between strings at those points. This is a profound philosophical shift. Space-time is not a container that strings exist in. Space-time is an emergent description of how strings relate to each other. The stage and the actors are the same thing. Or rather, there are no actors and no stage. There is just a network of relationships, and space-time is our way of organizing and describing those relationships. But if this is true, if space-time emerges from string relationships, then there might be situations where space-time itself breaks down or becomes meaningless. And indeed, string theory predicts such situations. Near singularities, or at very small distances comparable to the Planck length, the concept of space-time stops making sense. The strings continue to exist and interact, but they cannot be described as existing at particular locations in space anymore. This brings us to one of the most mind-bending ideas in string theory, the holographic principle. Chapter 16. The holographic principle. What I am about to tell you sounds like science fiction, but it is serious theoretical physics backed by rigorous mathematics. Are you ready? Here it is. The universe might be a hologram. The three-dimensional space you experience might actually be an illusion, a projection of information encoded on a distant two-dimensional surface. Let me explain how physicists arrived at this wild idea, because the journey is important. It started with a puzzle about black holes. In the 1970s, physicist Jacob Bekenstein realized something strange. If you throw a book into a black hole, all the information in that book seems to be lost forever. The book is gone. The words are gone. The information is destroyed. But quantum mechanics says information can never be destroyed. It can be scrambled, hidden, spread out, but never truly lost. This is called conservation of information, and it is as fundamental to physics as conservation of energy. So there was a paradox. General relativity, black holes, seemed to destroy information, but quantum mechanics said information must be conserved. Stephen Hawking initially believed information was destroyed in black holes, which would mean quantum mechanics was wrong in extreme situations. But Bekenstein had a clever insight. He calculated that black holes have entropy, a measure of disorder or hidden information. And here is the key. A black hole's entropy is proportional to its surface area, not its volume. This is weird. For normal objects, entropy depends on volume. A bigger box of gas has more entropy than a smaller box. But for black holes, it is the area of the event horizon, the surface of no return, that matters. It is as if all the information about what fell into the black hole is somehow stored on the two-dimensional surface of the horizon, not in the three-dimensional interior. It is like this. Imagine you write information on pieces of paper and throw them into a box. You would expect the amount of information stored to depend on the volume of the box. How much stuff can fit inside. But black holes are different. For them, the amount of information is limited by the area of the surface. It is as if the information is written on the surface, not inside. This led to a radical proposal called the holographic principle. Maybe the information about what is inside a region of space is actually encoded on the boundary of that region. The three-dimensional interior is like a hologram, a 3D image projected from 2D information. You have seen holograms before, those 3D images on credit cards or novelty posters. The image looks three-dimensional, but all the information is actually stored in a two-dimensional pattern on the surface. When you shine light on it at the right angle, the 3D image appears. The holographic principle says the universe might work the same way. Everything happening in a volume of space, every particle, every interaction, every event, might be fully described by information on the boundary surface of that volume. The three-dimensional space we think we inhabit might be an illusion, a holographic projection. This idea received stunning support in 1997 when string theorist Juan Maldacena proved a concrete mathematical example. He showed that a particular five-dimensional universe with gravity, described by string theory, is exactly equivalent to a four-dimensional quantum theory without gravity living on its boundary. Every question you can ask about the 5D universe can be answered by calculations in the 4D boundary theory. They are two different descriptions of the same reality. This is called the ADS-CFT correspondence, anti-de Sitter space conformal field theory correspondence, and it is one of the most important theoretical discoveries of the past 30 years. It is the most concrete realization of the holographic principle, and it has been tested in thousands of calculations. It works. So, what does this mean for our question about space-time? If space-time is holographic, then asking what it is made of is like asking what the 3D image in a hologram is made of. The image is not made of anything physical. It is made of information encoded on a 2D surface. The stuff is the information. The 3D space is just a convenient way to organize that information. In this view, space-time is not fundamental. It emerges from quantum information and quantum entanglement. When quantum bits, qubits, on the boundary become entangled with each other, they create the illusion of space between them in the bulk. More entanglement means more space. The geometry of space-time is encoded in the pattern of entanglement between boundary qubits. This is profound. It means space and distance are not fundamental properties of reality. They are derived concepts that emerge from something deeper: quantum entanglement. When two particles are strongly entangled, they are close in an emergent space-time. When they are weakly entangled, they are far apart. Some physicists summarize this with a slogan: space-time is quantum entanglement. ER-EPR is another related slogan. Einstein-Rosen bridges equal Einstein-Podolsky-Rosen pairs. It suggests that wormholes, ER bridges, connecting distant regions of space might be the geometric manifestation of quantum entanglement, EPR pairs, between particles. If this is right, then space-time is not made of tiny pieces of geometry. It is made of relationships, quantum correlations between fundamental degrees of freedom that we have not even fully identified yet. Space-time is woven from information and entanglement. But before you accept this as the final answer, I need to tell you about string theory's problems. Chapter 17. String theory's problems. String theory is mathematically beautiful. It unifies all particles and forces. It includes gravity naturally. It solves the infinity problems. It makes testable predictions about, wait, actually, that is the problem. String theory has not made testable predictions. Let me be clear. String theory makes mathematical predictions. It tells you how strings should behave. But translating those predictions into something we can measure in a laboratory has proven incredibly difficult. The reason is that string effects only become important at the Planck scale. energies about 10 pulses 16 times higher than anything we can produce in particle accelerators. We would need an accelerator the size of the galaxy to reach those energies. So string theory remains, for now, untested. We cannot prove it is right, and we cannot prove it is wrong. It exists in a frustrating limbo where it is mathematically consistent and beautiful, but empirically unverified. Problem number 2. The landscape problem. Remember how I said there are possibly 10 to the power of 500 different ways to curl up the extra dimensions. Each one gives a different universe with different physics. So which one is our universe? String theory does not tell us. It says pick one, but it does not give us a principle for choosing. Some physicists see this as a feature, not a bug. They say maybe all 10 to the power of 500 possibilities are real. They are all different universes in a vast multiverse. Our universe is just one where the constants happen to allow life to exist, and that is why we're here to observe it, the anthropic principle. But other physicists hate this answer. It feels like giving up on predicting anything. Problem number 3. String theory is hard. The mathematics is extremely complex. Even after decades of work, physicists do not fully understand string theory. They have made incredible progress, discovered beautiful connections, and solved many puzzles. But they still do not have a complete, non-perturbative formulation of the theory. What does non-perturbative mean? It means we currently understand string theory only by making approximations. We calculate what happens when strings interact weakly. But when strings interact strongly, the math becomes intractable. There might be entirely new phenomena, new phases of string theory that we are missing. Problem number 4. String theory has moved away from making contact with experiment. In the 1980s and 1990s, there was hope that string theory would predict new particles we could discover at the Large Hadron Collider, or explain subtle anomalies in existing data. But as the theory developed, those hopes faded. String theory became more abstract and mathematical, less connected to experimental physics. This has led to criticism. Some physicists, including Nobel laureates, have argued that string theory is not science anymore. It is mathematics masquerading as physics. Science requires testable predictions, they say, and string theory has not delivered. String theorists respond that the theory is still young, only about 50 years old, which is nothing compared to how long it took to develop quantum mechanics. They point to its mathematical consistency, its beautiful unification of forces, and its deep connections to pure mathematics. They argue that sometimes theory must run ahead of experiment, pointing to examples like the Higgs boson, predicted 50 years before discovery, or general relativity, verified decades after Einstein proposed it. Who is right? Time will tell. But string theory is not the only game in town. There is another approach that takes the opposite philosophical stance. Where string theory says space-time emerges from strings, loop quantum gravity says space-time is fundamental and is made of something concrete. Let us explore that now. Chapter 18. A different starting point loop. Quantum gravity, LQG, was born from a different philosophy than string theory. Instead of asking, what if particles are strings? LQG asks, what if we take Einstein's general relativity seriously and just apply quantum mechanics to it properly? Instead of replacing space-time with something else, LQG tries to quantize space-time directly. The founders of LQG, physicists like Abhay Ashtekar, Carlo Rovelli and Lee Smolin, believed that string theory was giving up on Einstein's greatest insight, that space-time is dynamical. In string theory, space-time emerges from strings. In LQG, space-time is fundamental and is itself quantized. Think about the difference in philosophy. String theory says, space-time is like water. It seems smooth and continuous, but it is really made of molecules, strings, that we just cannot see. LQG says, space-time is like electromagnetic fields. It is genuinely quantum, with discrete states and quantum uncertainty at small scales. LQG starts with Einstein's general relativity, but rewrites it in a different mathematical language called connection dynamics. In this formulation, instead of describing the curvature of space-time directly, you describe something called the connection. Roughly, a mathematical object that tells you how to compare things at different points in space. This might sound technical, but here is why it matters. When written in this way, Einstein's equations look much more similar to the equations for other quantum fields. And that makes it possible to apply standard quantization techniques. LQG physicists followed a procedure similar to what was used to quantize the electromagnetic field, but they applied it to the gravitational field. What came out of this quantization was stunning. Space itself is made of discrete, quantized units. Space is not continuous. It is grainy. At the smallest scales, space is woven from quantum threads called spin networks. Imagine space as a three-dimensional spider web made of quantum threads. Each thread connects nodes in the network. The threads carry quantum information about area, and the nodes carry quantum information about volume. This spider web is space. Space does not exist as some background that the web sits in. The web is space. The threads are not in space. They create space by their connections. Just as a fishing net creates a surface not by sitting on some pre-existing surface, but by the connections between threads, a spin network creates space by its structure of connections. And here's the key point. The threads are quantum. They exist in superpositions. They can be entangled. They obey Heisenberg uncertainty principles. Space at the smallest scales is fundamentally quantum and discrete. Let me give you concrete numbers. Each elementary loop in a spin network has an area of about 1 Planck area, roughly 10 to the power negative 70 square meters. That is incomprehensibly tiny. You could fit about 10⁻70 of these loops side by side across a single proton. These loops are the atoms of space, the smallest indivisible units of area. Similarly, each node in a spin network represents a quantum of volume, about 10 to the power minus 105 cubic meters. This is the smallest possible volume. You cannot subdivide space any smaller than this. There is no meaning to a distance smaller than a Planck length or a volume smaller than a Planck volume. This answers our question directly. What is space made of? In loop quantum gravity, space is made of quantum spin networks. These are not objects in space, they are space. The smooth, continuous space we experience emerges from countless tiny quantum loops woven together, just as a smooth beach emerges from countless grains of sand. But we still need to understand how time fits into this picture. Chapter 19. The Atoms of Time. If space is quantized, made of discrete chunks, what about time? Does time also come in discrete ticks like frames in a movie? Loop quantum gravity says yes. But to understand this, we need to realize something subtle. In general relativity, there is no absolute time ticking in the background. Time is part of space-time, and space-time is dynamical. The question, what time is it, does not have an absolute answer. It depends on your motion and the gravitational field around you. LQG takes this seriously. In LQG, time is not a background parameter. Instead, time emerges from change, from how the quantum geometry of space evolves. Here's the picture. Remember, a spin network is a snapshot of the quantum state of space at one instant. But spin networks are not static. They evolve. Threads can split and merge. Nodes can appear and disappear. The network constantly reconfigures itself. This evolution creates what we perceive as the flow of time. To describe this evolution, LQG uses structures called spin foams. If a spin network is a 3D spider web representing space at one instant, a spin foam is a 4D structure representing the history of how that spider web evolves. Think of it like this. A spin network is a single photograph, while a spin foam is a video. It shows how things change. In a spin foam, the threads of spin networks become 2D surfaces and the nodes become 1D threads. The whole structure is four-dimensional, 3 space dimensions plus time. Each sheet or face in the foam represents a quantum event, a discrete change in the geometry of space. And here is the key. These events are discrete. Space-time in LQG is not smooth at small scales. It is made of individual quantum events, each representing a tiny change in geometry. Time does not flow continuously. It proceeds in discrete quantum jumps, each lasting about 1 Planck time, which is equal to 10 to the power of minus 43. This is radical. It means that at the deepest level, time is not continuous. There is a shortest possible duration. You cannot subdivide time infinitely. There is a smallest meaningful tick of time, just as there is a smallest meaningful volume of space. Now you might ask, if time is discrete, why does it seem continuous to us? The same reason space seems continuous even though it is made of atoms. The Planck time is so short that even the fastest processes we can measure involve trillions upon trillions of Planck times. It is like watching a movie at 1043 frames per second. You would never notice the individual frames. But there is something even more radical here. In LQG, time is not fundamental. What is fundamental are the causal relationships between events. Which events can influence which other events? These relationships create a partial ordering of events, and that ordering is what we perceive as time. Think of it like a family tree. The tree does not exist in some pre-existing time framework. The relationships create the temporal structure. Before and after only make sense in terms of ancestry. Similarly, in LQG, before and after only make sense in terms of causal relationships between quantum geometry events. This resolves one of the deepest puzzles in quantum gravity. How do you do quantum mechanics when time itself is quantum? Answer: you do not use time as a background parameter. Instead, you describe how quantum states of geometry are related by causal connections. Time emerges from those relationships. So to summarize, in loop quantum gravity, what is spacetime made of? It is made of quantum geometry, discrete quanta of area and volume, woven into spin networks and evolving through spin foams. Space and time are not continuous. They are grainy at the Planck scale. They are not fundamental. They emerge from the relationships between quantum geometric events. This is a very different answer than string theory's answer. String theory says space-time emerges from strings. LQG says space-time is made of quantum geometry. Space-time quantizes itself. Both are mathematically consistent theories, but they start from different philosophical premises and arrive at different pictures of reality. Now let us see what predictions LQG makes and what problems it faces. Chapter 20. LQG's predictions. Unlike string theory, loop quantum gravity makes several concrete predictions that could potentially be tested. Let me tell you about the most important ones. First, black hole entropy. Remember how we talked about black holes having entropy proportional to their surface area? This was one of the great mysteries. Why should entropy depend on area rather than volume? LQG provides an answer. In LQG, the event horizon of a black hole is itself a spin network, a quantum surface made of discrete area quanta. Each quantum of area can be in different quantum states, and the number of possible states gives the entropy. LQG physicists calculated this entropy and got a result that matches Bekenstein and Hawking's prediction. This was a major success for the theory. Second, the Big Bounce. In general relativity, if you run time backward from the current expanding universe, you reach a singularity, the Big Bang, where density and curvature become infinite. But infinities signal that the theory has broken down. In LQG, the singularity disappears. Here is why. As you compress space to smaller and smaller sizes, quantum effects become stronger. At the Planck scale, quantum geometry becomes so important that it prevents further compression. Space literally cannot be squeezed smaller than the Planck volume. So what happens instead of a Big Bang singularity? A big bounce. LQG suggests the universe did not begin from a singularity, but rather bounced from a previous contracting phase. Before our universe expanded, there was a previous universe that was contracting. When it reached the Planck density, quantum geometry effects caused it to bounce, to reverse direction and start expanding. That expansion is what we call the Big Bang. This is beautiful because it removes the singularity problem. The universe did not come from nothing. It transitioned from a previous phase. Time might be eternal, with cycles of expansion and contraction, each bounce creating the illusion of a beginning. Third, discrete spacetime effects. If space-time is discrete, there might be tiny violations of the usual rules at extreme energies. For example, light at different wavelengths might travel at slightly different speeds. Not because they move through space differently, but because space itself is grainy and affects different wavelengths differently. These effects would be incredibly tiny, but possibly measurable using gamma-ray bursts from distant galaxies. Physicists are looking for such effects in data from gamma-ray telescopes. So far, no violations have been found, which puts some constraints on LQG, but does not rule it out. Fourth, cosmological implications. LQG makes predictions about the very early universe that might show up in the cosmic microwave background, the faint glow of radiation left over from the early universe. Some versions of LQG predict particular patterns in this radiation that differ slightly from standard predictions. These might be testable with future satellite observations, so LQG is more connected to potential experimental tests than string theory. But it has problems too. The biggest problem: LQG has struggled to recover Einstein's general relativity in all situations. When space-time is nearly flat and quantum effects are weak, LQG should reduce to Einstein's equations. And in many cases it does. But proving this rigorously in all cases has been difficult. There are mathematical subtleties and ambiguities that have not been fully resolved. Second problem: LQG focuses on quantum gravity, but does not naturally include the other forces and particles. String theory unifies gravity with electromagnetism and nuclear forces. LQG does not. It is purely a theory of quantum geometry. You have to add matter and other forces by hand. This feels less elegant and unified. Third problem: like string theory, LQG operates at scales we cannot directly probe. We cannot build microscopes powerful enough to see spin networks. We can only test indirect consequences of the theory. Despite these challenges, LQG represents a genuinely different approach to quantum gravity, and many physicists find it compelling. It gives a direct, concrete answer to our question. Space-time is made of something: quantum geometry woven from spin networks. But there is yet another approach that is even more radical. Some physicists think both string theory and LQG might be starting from the wrong assumption. Maybe space-time is not fundamental at all. Maybe it is an emergent illusion that appears only at large scales. Let us explore this idea. Chapter 21. Space-time as illusion. What if everything we have been talking about, all of space-time, all of reality as we know it, is an illusion? Not an illusion in the sense that it does not exist, but an illusion in the sense that it is an emergent phenomenon that appears only at large scales and disappears when you zoom in far enough. This is one of the most radical ideas in modern physics, and it is gaining support from theoretical work in string theory, quantum information theory, and other areas. The idea is that space and time are not fundamental features of reality, but rather emergent properties that arise from something deeper. Let me explain what emergent means with an example you already understand. Temperature. When you hold a cup of hot coffee, you feel warmth. Temperature seems like a fundamental property. The coffee is hot. But zoom in to the molecular level, and temperature disappears. Individual molecules do not have temperature. They just move at various speeds. Temperature is a statistical property that only makes sense when you have many molecules moving around. It is the average kinetic energy of countless molecules. For a single molecule, temperature is meaningless. Temperature emerges from collective behavior. Similarly, consider pressure. Air pressure pushes on your skin, but individual air molecules do not have pressure. Pressure is the collective effect of countless molecules bouncing off a surface. It emerges from statistics. What if space and time are like temperature and pressure? What if they only appear when you look at large collections of something more fundamental, but disappear when you zoom in to the fundamental level? This idea is supported by theoretical discoveries in string theory, particularly the holographic principle we discussed earlier. Remember, in holographic theories, space-time in the bulk, the interior, emerges from quantum theory on the boundary. The boundary theory does not have space. It is a quantum field theory living on a lower dimensional surface. Yet somehow, from the quantum interactions on that surface, an entire dimension of space emerges. How does this work? The key is quantum entanglement. When quantum particles become entangled, when their states become correlated so that measuring one instantly affects the other, they create connections. These connections might literally be what we perceive as space. Imagine two qubits, quantum bits, on the boundary of the holographic universe. When they are highly entangled, strongly correlated, they correspond to points in the bulk space-time that are close together. When they are weakly entangled, they correspond to points that are far apart. The geometry of space, the distances between points, is encoded in the pattern of entanglement between boundary qubits. This leads to a stunning insight. Space is quantum entanglement. The threads that weave the fabric of space-time are not physical threads. They are threads of quantum correlation. Distance is not fundamental. It is a measure of how entangled things are. Physicists Mark van Ramsdonk and others have shown that you can build space from entanglement. Start with qubits that are all completely entangled with each other, maximally connected. This creates a highly curved, compressed space. Now gradually reduce the entanglement between some qubits. As you do, space expands between them. Less entanglement means more spatial separation. This even explains wormholes. A wormhole is a bridge connecting two distant regions of space. The famous ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that Einstein-Rosen bridges, wormholes, are the geometric manifestation of Einstein-Podolsky-Rosen pairs, entangled particles. Two entangled particles are not just correlated. They are literally connected through space-time via a microscopic wormhole. If this is right, then asking, what is space-time made of, is like asking, what is temperature made of? Temperature is not made of anything. It is an emergent statistical property. Similarly, space-time is not made of stuff. It is an emergent description of quantum entanglement patterns. This has philosophical implications that are hard to overstate. It means the space around you, the distance between your hand and your screen, is not real in a fundamental sense. It is a convenient description that appears at large scales, but it breaks down at the quantum level. At the deepest level, there is no space, just quantum information and quantum correlations. Some physicists go even further and suggest that time also emerges from entanglement. In this view, the flow of time, the feeling that moments pass one after another, might be related to the increase in entanglement entropy. As quantum systems interact and become more entangled, entropy increases. We perceive this increase as the flow of time, the arrow of time pointing from past to future. This is deeply strange, but surprisingly compelling, and it connects to other approaches that suggest space-time is emergent. Let us look at one more: causal set theory. Chapter 22. Causal set theory. Here is yet another radical idea about what space-time might be made of: events and causal relationships. This approach is called causal set theory, and it takes a completely different starting point from both string theory and loop quantum gravity. The founders of causal set theory, Raphael Sorkin and others, asked a simple question: what is the minimum information you need to reconstruct space-time? You need to know which events can influence which other events. That is it. Everything else, distances, times, geometry, can be derived from knowing the causal structure. Think about it this way. Imagine the entire history of the universe as a collection of events. Your birth is an event. The moment you started reading this is an event. The explosion of a distant star 1 billion years ago is an event. Now, some events can influence other events because they are connected by a path traveling at or below light speed, while others cannot because they are too far apart in space-time. This web of influence, which events can affect which others, is called the causal structure of space-time. And causal set theory proposes that this causal structure is the fundamental thing. Space-time geometry emerges from it. Here is how it works. Imagine a causal set as a collection of points, events, with arrows between them showing which events can influence which. Event A has an arrow pointing to event B if A is in B's causal past, if A could have influenced B. You build up a network of such relationships. Now, if you have many events, a huge network, you can start to extract geometric information. The distance between two events is related to the number of intermediate events in the causal chain connecting them. The volume of a region is related to the number of events in that region. Geometry emerges from counting events and causal relationships. But here is the key. The set of events is discrete, not continuous. Space-time is fundamentally made of individual, indivisible events, each separated from its neighbours by about 1 Planck time and 1 Planck length. Just like loop quantum gravity, causal set theory says space-time is grainy at small scales. The difference is philosophical. Loop quantum gravity starts with Einstein's equations and quantizes them, finding that space is made of spin networks. Causal set theory starts with the idea that causality is fundamental and finds that space-time emerges from causal ordering. One beautiful feature of causal set theory. It explains the arrow of time naturally. In a causal set, relationships only go one direction, from cause to effect, never backward. This built-in directionality automatically gives you a flow of time. Past and future are not arbitrary labels, they are built into the causal structure. Another nice feature. Causal sets might explain why space-time is four-dimensional, 3 space, 1 time. Raphael Sorkin and colleagues have done calculations suggesting that 4 dimensions is the most natural dimensionality that emerges from random causal sets. Other dimensions are possible, but less likely. If true, this would answer a question Einstein never answered. Why does space-time have 4 dimensions and not 5 or 6? The downside? Causal set theory is less developed than string theory or loop quantum gravity. It has made fewer concrete predictions and has not yet been fully worked out mathematically. It remains an active area of research, but is not as far along as the other approaches. Still, it represents an important alternative perspective. Maybe the fundamental reality is not strings, not quantum geometry, but simply events and their causal relationships. Everything else, space, time, distance, geometry, emerges from that simple foundation. Chapter 23. The Information Theory Approach. Now we come to perhaps the most radical idea of all. What if the most fundamental thing is not matter, not energy, not space-time, not even quantum fields, but information? Pure, abstract, mathematical information? This idea has a famous advocate, the late physicist John Archibald Wheeler, who coined the phrase, "it from bit." The it means physical reality, matter, energy, space-time, everything. The bit means information, binary digits, zeros and ones, yes or no answers to questions. Wheeler suggested that every physical quantity, every property of every particle, every measurement of every field, ultimately boils down to information. When you measure an electron's spin, you get a bit of information, spin up or spin down. When you measure a photon's polarization, you get a bit horizontal or vertical. Everything physical is, at bottom, made of answers to yes or no questions. In the quantum version of this idea, we have qubits instead of classical bits. A qubit is a quantum system that can be in a superposition of 0 and 1 simultaneously. Qubits can be entangled, creating correlations that have no classical analogue, and the entire universe might be, at its deepest level, a vast quantum computer processing qubits. This connects directly to the emergence of space-time we discussed earlier. If space emerges from quantum entanglement, and entanglement is a property of quantum information, then space is made of information. The stuff of reality is not material stuff. It is informational stuff. Recent work has strengthened this connection. Physicists have discovered relationships between the geometry of space-time and the complexity of quantum states. Here is what I mean by complexity. Imagine you have a quantum computer in some simple starting state, all qubits set to 0, say. Now you run a quantum computation, applying gates that entangle qubits and create correlations. The system state becomes more complex. It takes more computational steps to prepare it from the starting state. Remarkably, this quantum computational complexity seems to be related to the volume of space in holographic theories. As the boundary quantum state becomes more complex, the volume of space in the bulk interior grows. It is as if space is literally being created by the increasing complexity of quantum information processing. This leads to a wild idea. Maybe the expansion of the universe, the fact that space is getting bigger, is related to the universe's quantum state becoming more complex over time. Space grows because quantum information is being processed and complexity is increasing. Some physicists have even suggested that space-time itself might be a quantum error-correcting code. In quantum computing, error correction codes protect quantum information from noise and decoherence. They do this by encoding information redundantly across multiple qubits. Interestingly, holographic spacetimes have properties very similar to quantum error-correcting codes. Information is encoded redundantly in the bulk spacetime, protected from errors. If spacetime is an error-correcting code, this might explain its robustness. Despite quantum fluctuations at the Planck scale, spacetime appears smooth and stable at larger scales. Maybe this stability comes from error correction, the redundancy built into how information is encoded geometrically. All of this is still speculative and under active research. But it points toward a stunning conclusion. The fabric of space-time might not be woven from strings or quantum loops or causal events. It might be woven from information itself. Space-time might be the way the universe organizes and processes quantum information. If this is true, then the question, what is space-time made of, has a profound answer. It is made of the same thing your thoughts are made of, the same thing a computer program is made of, the same thing a mathematical proof is made of. Information. Not information about physical things. Information is the physical thing. There is no distinction between the map and the territory. Reality is information, and information is reality. This is as deep as the rabbit hole goes. And it brings us to the final question. Where do we stand? Chapter 24. Where do we stand? We have journeyed together through 3 hours of mind-bending physics. We started with a simple question. What is space-time made of? And we have explored multiple answers. Vibrating strings, quantum loops, causal sets, quantum information, or some combination we have not thought of yet. So, what is the true answer? Let me be completely honest with you. We do not know. Not yet. Despite decades of brilliant work by thousands of physicists, we do not have a final, verified answer to this question. But here is what we do know. Space-time is real. It is not just a mathematical abstraction or a coordinate system. Space-time has physical properties. It can bend, stretch, compress, and wave. We have measured these effects directly with gravitational wave detectors. Space-time responds to mass and energy, and it affects how matter moves. It is as real as any field in physics. We also know that space-time must have a quantum description. At the Planck scale, 10 to 35 meters and 10 to 43 seconds, quantum effects become dominant. The smooth, continuous spacetime of Einstein must give way to something else. Whether that something else is quantum foam, spin networks, strings, or pure information, we do not yet know. But it must be something. We know that spacetime is probably not fundamental. All signs point toward spacetime being emergent, appearing at large scales but breaking down at small scales. This is a profound shift in perspective. For centuries, we thought space was the eternal stage where reality unfolds. Now it looks like space itself is a performance, a show that appears only when you step back far enough. So where does the evidence point? The honest answer is multiple directions. String theory is mathematically beautiful and naturally unifies all forces, but it is hard to test and has the landscape problem. Loop quantum gravity is more directly connected to general relativity and makes some testable predictions, but struggles to recover Einstein's equations in all cases and does not include other forces elegantly. The emergence from information approach is philosophically compelling and connects to cutting-edge research in quantum information and holography, but it is still in early stages of development. Causal set theory offers an elegant starting point, but needs more mathematical development. Different physicists bet on different horses. The string theory community is large and active, making continuous progress on mathematical fronts. The loop quantum gravity community is smaller but dedicated, pushing forward on quantum geometry. A growing number of physicists are exploring the information theoretic approach, inspired by connections between quantum information and space-time. What would it take to decide between these theories? We need experimental evidence. We need to detect quantum gravitational effects, something that shows us what space-time is really like at the Planck scale. But this is incredibly difficult because the Planck scale is so small. However, there are some possibilities. We might detect subtle violations of Lorentz symmetry, the principle that physics looks the same in all directions, in high-energy cosmic rays. Some quantum gravity theories predict tiny violations. We might see unexpected patterns in gravitational waves from extreme events like black hole mergers. We might find subtle effects in the cosmic microwave background radiation from the early universe. We might detect quantum effects of gravity in laboratory experiments using ultra-cold atoms or quantum interference of massive molecules. Several groups are working on experiments that might detect quantum gravitational effects, though these are extremely challenging. Or we might get lucky. We might discover something completely unexpected, a phenomenon that forces us to accept one theory over the others, or inspires an entirely new theory we had not thought of. The truth is, we are living through an exciting time in the history of physics. For the first time, humans are seriously asking, what is reality made of at the deepest level? Not just what are particles made of, but what is the stage itself made of? What is space? What is time? These are questions that philosophers have asked for millennia, but now physicists have mathematical tools to actually answer them. 50 years from now, or 100 years from now, physicists will look back at this era and say, that was when humanity figured out the true nature of space-time. They might laugh at some of our theories that turned out wrong, but they will also marvel at how close we came with others. And you, yes you, watching this video, you are witnessing this golden age. You are living through the time when humans are discovering the deepest secrets of reality. That is incredible. Chapter 25. The Philosophical Implications. Before we end, I want to step back and think about what all of this means. Not just for physics, but for how you think about yourself and your place in the universe. If space-time is made of quantum loops or strings or information, what does that say about you? Well, you exist in space-time. You move through space-time. Your entire life, from birth to this moment to your eventual death, is a path through space-time, what physicists call your world line. If space-time is woven from quantum threads, then you are a pattern in that weaving. You are not separate from space-time, you are part of it. Your atoms, your molecules, the electrical signals in your brain, all of these are vibrations in quantum fields, dancing across the fabric of quantum space-time. If space-time emerges from quantum entanglement and information, then you are ultimately a pattern of information. Quantum information organized in a particular way that creates consciousness, memory, personality. You are a story written in the language of quantum correlations. This is not meant to make you feel small or meaningless. Quite the opposite. It means you are intimately connected to the deepest structure of reality. The universe is not a dead, mechanical thing with you as an accidental byproduct. You are the universe becoming aware of itself. You are space-time examining space-time. Carl Sagan said it beautifully. We are a way for the cosmos to know itself. The atoms in your body were forged in the hearts of stars. The quantum fields that make up your particles extend throughout all of space. The space-time that curves around your body is the same space-time that curves around black holes and galaxies. You are not in the universe. You are the universe, in a very localized and aware form. Understanding what space-time is made of is not just abstract science. It is understanding what you are made of at the deepest level. It is understanding the stage where every moment of joy, every connection with another person, every thought you have ever had, takes place. And here is something beautiful. We do not have the final answer yet, which means the mystery continues. There is still wonder to be found. There are still discoveries waiting. The universe has not revealed all its secrets. It is still hiding the deepest ones, waiting for clever humans to figure them out. Maybe one of you watching this will be the person who solves it. Maybe you will have the insight that finally shows us what space-time is truly made of. Or maybe you will inspire someone else who makes the discovery. Or maybe you will simply appreciate the beauty of the question and the journey we have taken together. Because that is what science is really about. Not just finding answers, but learning to ask better questions. Learning to wonder. Learning to see the universe not as a boring, explained thing, but as an infinite source of mystery and beauty. So here is my final thought. Every time you look around the room you are in, remember you are looking at space-time. The emptiness between you and the wall is not truly empty. It is woven from quantum threads too small to see, or vibrating strings, or patterns of entangled information. It can bend and wave and dance. It is dynamic and alive in a sense. The space around you is as real and as mysterious as the most distant galaxy. And we are slowly figuring out what it is made of. We are unraveling the deepest secret of existence itself. Is it made of strings, loops, information? We will find out. And when we do, it will be one of humanity's greatest achievements, understanding not just what stuff is made of, but what reality itself is made of. Thank you for taking this journey with me. Thank you for having the patience and curiosity to think about these deep questions. If this video changed how you see reality, even just a little, then it was worth every minute. And remember, the next time someone says the fabric of space-time, you can ask, but what are the threads? Now you know what physicists are trying to figure out. And you know it is one of the deepest, most beautiful questions humans have ever asked. Keep wondering. Keep questioning. Keep looking up at the stars and asking why. Because that is what makes us human. That is what makes us alive.